The third speaker today is from the Mechanical Engineering Department, Professor Pande, and I will request Professor Kulkarni to please introduce the speaker.
So, Professor Pande has been with the Mechanical Engineering Department for a very long time now. He joined the institute as a faculty in 1981, and since then he has been working in an area which is still very much needed and required. So the primary area of his research is computer-aided design and manufacturing, CAD/CAM as it is known. And within this domain, he has extensively worked in geometric reasoning of CAD models using AI techniques, feature recognition, neural networks and genetic algorithm applications, computer-assisted process planning for multi-axis CNC machines, efficient algorithm for additive manufacturing, which is going to be the topic that he would be talking about. Computational metrology, internet-based product design and manufacture, modeling and simulation of manufacturing, especially machining processes. If you look at all these topics, these actually form the core and heart of what we today call as smart manufacturing. None of the things that we talk about in smart manufacturing will work if these things are not addressed at the algorithmic level. So I would say that this covers probably 30 to 40% of what smart manufacturing is all about as a generic thing. Of course, he has published a very large number of publications, all are well cited, and he even received the IIT Bombay Research Publication Award. What to me is also equally more important is that from all his research, I have seen that products have come out which the industries can actually use to solve problems. Out of which two have resulted into technology transfers. One is the WebNC software, which is for internet-based collaborative system for intelligent CNC machining. And another one is F-Turn, which is feature-based process planning system for CNC turning. This has been successfully transferred to the industry and is now commercialized for the industry usage. So with this, I will hand over the platform to Professor Pande and request him to deliver his talk. Thank you.
Thank you, Professor Kulkarni, for this nice introduction. At the outset, I would like to thank IRCC and IIT Bombay for giving us this award as a team, and it will be my endeavor to present the highlights of our research in this area, a very general presentation where I would like to share with some of the important considerations which went into thinking about this methodology and going about it as a part of our research. The theme is efficient process planning strategies for additive manufacturing. Today, the additive manufacturing is a new word which has been used from the turn of this century, and as we find that it is cutting across almost all the branches where the school children, everybody knows and talks about it. Variety of things which we call as 3D printing. It started with the name rapid manufacturing, rapid prototyping, now 3D printing and several of those things. It is what is termed as a disruptive technology, completely different from the traditional manufacturing technology, in which you can see that this is a technology to fabricate part layer by layer directly from the CAD model. It's not other type of technology where you try to disseminate part, disassemble, then assemble and so on. Directly from the CAD model, you fabricate the whole thing in a layer by layer. There are many processes which have been developed, which are typically called as stereolithography, fused deposition modeling, selective laser sintering, 3D printing, and so on and so forth. As you can see, that's primarily targeting into the production of the component in the material of fabrication. Otherwise, the technology remains the same, as we would see, and that's why this technology has very wide expected applications, industrial applications, which are typically in prototyping, because that's where the product development starts, with a prototype. Then there are expendable patterns which are used in precision casting processes. You have the biomedical parts, namely in the healthcare. Practically it gets into every complex part of automobile, aerospace and even in the microfabrication industry. So it has very large number of applications which will there. Before we plunge into what is our research and what we have been trying to do, a few words about the additive manufacturing technology itself. This is a route, a process route, how a part is fabricated directly from a CAD model in a layer by layer fashion. As you can see that you start at the left end with a CAD model, which is a nice model which is developed in the three-dimensional space, which you can see, which you can orient, which you can calculate the properties about. You also have a good rendering of the model. You do finite element analysis, so on and so forth. But here we are taking it from art to part. The fundamental route is from art to part. So you take the CAD model, and then at the right hand you see the machine, which is the additive manufacturing machine. There are large number of such machines which are available, which are being developed by the industry, and that's why this is a hotly pursued area of research by the academicians as well as the research community. And you can see that this typical machine, when you consider, has a table on which the part is built in a layer by layer fashion. The table can move up and down, also it can move X and Y in the space. There is a head. The head can be of different type. It can be a laser head, it can be an electron beam, it can be a fused deposition type of a modeling in which there is some deposition and so on. But the part is built in a layer by layer fashion, which is shown below, which shows that a part is cut into specific layers which are built one on the top of another and glued together so that the part is completely built. It's very important to observe that the profile which is produced for such component is essentially approximated profile which has a stair-step pattern, and that is one of the fundamental reasons where the part quality which is produced by this type of thing is not very accurate compared to the traditional technology. Though we find that additive manufacturing is a very good process which has significantly cut down the production time from the product to the kick-off stage, or what we term as the product development cycle time, but it has several basic limitations which actually form the challenges for this particular thing. First and foremost, it has very low productivity. It has a very large build time, primarily because the component is built layer by layer, and that makes the part cost very high. That's one of the limitations why today we cannot just go to getting to the situation, say that, look, there is an additive manufacturing, overnight I would like to shift to additive manufacturing. It's not possible because of low productivity, very high cost. It has a low part quality also, primarily because of the stair-step error as we have seen. Plus there is a thermal phenomena which causes it warpage and shrinkage, which needs to be taken care. The third point is that it has low material utilization, primarily because when the part is built layer by layer, some of the overhung parts are to be supported during the process of manufacture, which are required to be broken off and thrown away, which means the yield of the component is much less. And that's essentially the reason why the material utilization is poor, because certain part of the process material which is built has to be thrown off. And the last and the most important point is the situation that it fabricates a part today in the non-functional materials. For example, if you take a thing, we are choosing a material or a heat transfer or a process or heat treatment to suit the product function. But here we are building the part just for the purpose of prototyping, which are many times built in nylon, ABS, ceramics, polymers here and there, which are not the functional materials which are actually used into the component or the assembly. So these challenges need to be addressed, and it is here the real research and the industry challenge comes into picture. So our research focus has been primarily on the computational domain, that is when we start from the CAD model, then we get into the process planning, which acts as a bridge between design and manufacturing, and the tool path what it produces is finally given to the additive manufacturing machine, which essentially produces the component. Here what we are trying to address is to develop, which we have proposed, and I will be presenting some results about it, is the optimum process planning strategy for improving three important aspects, namely the process productivity, namely the build time, the part quality, which is the stair-step error, and the third one is the material utilization. So our focus has been on two key issues which we are trying to do. There are a whole lot of issues which need to be addressed as we have seen, but two key issues we are focused upon. One is the hollowing of the CAD models, and the second one is optimum part orientation using the genetic algorithms. Let me spend few words on what is hollowing. First a question comes is, why hollow a part? The primary reason is that if you look at a component which is being made today, if you hollow a part, it is obvious that the material which you are spending on that will be much less. So the build time will be very fast, cost will be much less, but the hollowing has to be essentially done in order to see that the part performs the function what it is expected to do. That means strength becomes important. You would like to hollow as much as possible, but commensurate with the strength and the function the part is supposed to perform. Now if you look at this situation, this shows the typical situation of hollowing. You have a CAD model which is designed in the three-dimensional space XYZ. The part is oriented as you go in the middle of the figure, and on the oriented part, then you do a slicing which is as per a plane parallel to the base of the machine, namely in the XY. That red line which gives you the slicing of the plane, and the slicing essentially creates a profile which is in the XY, which is the build layer or the slice layer. Hollowing is the process of offsetting the outside profile inwards or imploding in such a way that you are creating a shell, and this particular shell is essentially sustains the part. So the hollowing, which is nothing but a profile offsetting operation. A part is hollowed. When you are hollowing a part, the inside profile is not that important. It is just for saving the material. But the outside profile is still very important, and if you are using that as a pattern which is essentially built or which is essentially used for creating a very sustainable or expendable pattern, you will see that outside profile has to be very accurate, because that's where the part is needed. Inside profile is just for an approximate profile but saves the material. So what we have essentially developed in our research is a virtual workbench. I will call it as a virtual workbench, essentially a software in which a large number of modules are there, in which the user can input the CAD model, what he is interested in fabricating, and there are various modules which are written in various algorithms. I will be glad to share with, but here I am just giving you a conceptually what has been going on in each of the module, and we'll come back to the results. So these particular modules essentially give a virtual workbench in which a person can operate all these things, tune the parameters. It can also create the tool path finally, which leads to the machine, and that particular path will drive the machine in order to create the component. So from arc to part, this is the way it goes. So we will talk of hollowing algorithm. We have explained the process. What is hollowing? It is basically imploding the external profile in a layer. So first it inputs the CAD model. Then from the user, it takes the parameters. What is the part orientation for fabrication? To begin with, it has to do that. But as we'll put into the second module, which is essentially the module for optimum part orientation, this part will be automatically coming from the second module, which means that for a given part oriented, it asks for the wall thickness. That is, how much should be the material to be left as a shelling material. It also gives the slice thickness. Part is built layer by layer, so the slice thickness is extremely important, because that decides the part accuracy, also that decides the part build time. Taking these three inputs, it voxelizes the oriented CAD model. What is voxelization? Voxelization is a process of approximating the exact geometry into voxels. A voxel is an equivalent of a pixel. I call it as a sugar cube. Look at something like a sugar cube. That is a typical voxel or a cuboid. So you consider that three-dimensional complex part is actually voxelized. That means considered as if you have sugar cubes which are glued together in order to make a particular component. So voxelize the model, then that model is sliced and that is offsetted in order to get to the situation of determination. We use variety of models in order to test our algorithms. These are all derived from Stanford Graphics Library, because they are the most complex models which have been put in the public domain for testing the algorithms. So we have tested our algorithms with those type of models. This is a Stanford bunny, and then you have the horse, you have the squirrel. What is written below are the number of facets. Engineering components are typically pretty simple, because you have surfaces which are made up of either flat planes or cylindrical or at the most spherical surfaces. Complex freeform surfaces are rarely there into the engineering components, though there are into situations which are coming, but art models, as they are called, are very, very complex models. So we wanted to test our algorithms on them so that they are automatically available and they are applicable to the simple parts. So these are the models which we picked up, some typical models as I am showing, a cow, a biomedical part, and so on. Again the facets. We chose two processes in order to test our algorithms. First is the SLS process, selective laser sintering, and another one is the fuse deposition modeling. The reason for choosing these two processes are like this, that if you go to laser sintering, it is a powder based additive manufacturing process which does not need the support structures. Whereas if you go to fuse deposition modeling, it has a head which actually gives deposition of the melted wire or melted type of thing, which is as a gun and it deposits on the top of that. So those type of things need support structures, and where the material utilization is primarily being done. So the two processes for which the algorithms have tested would automatically mean that they are applicable to all range of processes which need support, which do not need support. So moving further, this typically shows the hollowing, how the algorithm essentially works out and gives the thing. You have, for example, a cow model, a particular layer is taken, it is voxelized, and with a shelling thickness what has been given, it is imploded so that you get the contours which are essentially there based on the wall thickness commensurate with the strength of the component. Shows the squirrel model, where also in a layer it shows the typical hollowing operation. At each layer, what finally emerges is a scenario like this, where the outer layer, which is shown in blue, is the one which is coming from the exact model, having those many number of facets which are obtained by means of geometric algorithms, essentially work on them, oriented model, the slicing, and the blue contour, which is exact contour, because that is what is going to be determining the part accuracy. The inside contour is coming from the voxel model, because functionally it is not important, so its approximate profile is good enough. And you can see that the volume of the hollow model is primarily based on the area between the two contours and the layer thickness what you have chosen. Summed up over entire layers gives the volume of the hollow model. Let me shift the gear at this stage and get on to part orientation, which is essentially one of the very important operations in this virtual workbench. The part orientation actually governs what you say three fundamental parameters, namely the part build time or the build height. As you know that as the part is oriented, the height can go on changing within the envelope from maximum height to minimum height. You can orient a part. As you orient the part, you can see that the stair step error will be coming, because everywhere you will have the approximated stair step error. And since you are first orienting and then slicing and then hollowing, you would come to the stage where the volume of the hollow model will be there. Our objective is to optimize, to see that minimize all the three parameters. What professor has told some time back, multi-parameter, here is actually the practical situation where you would really like to have minimization of all the three parameters, the build height or the build time. Another situation is the stair step error, and the third one is the percentage utilization. You can see that mathematically the problem essentially gets that for a given model, you need to compute optimum values of theta x and theta y, how the model can be rotated around x axis and the y axis, which forms the orientation. So that essentially is the optimum focus of the whole thing. How did we propose the optimization problem? Is we propose the optimization function or objective function f, which is a weighted function of the three fundamental process parameters, namely h, r and pm. These are the three fundamental process function parameters called as part build height, the stair step error, and the utilization factor of the material, which we call as pm, which is nothing but the volume of the hollow model to the volume of the solid model. So these three are combined together by weightages w1, w2, w3, which collapse into a single objective function f, and we optimize f in order to get optimization of all the three, which as we know is very difficult, because you cannot have, if you catch one, the other one runs away, if you catch second one, the first runs away. So we need to have an integrated approach in order to come to this particular situation, how we can optimize this. The process performance parameters which have been essentially put up are normalized, because we don't want a bias in the optimization. If you have, because their dimensions are different, stair step error will be in microns, build height will be something, third is the ratio. So we wanted to keep the whole thing in a normalized fashion so that there is no bias of any particular kind. And that's essentially we put the normalized parameters where the actual build height upon certain dimensions of the bounding box. Then we found out the stair step error, and that is normalized. And third is the percentage utilization of the material, which essentially tells you volume of the hollow divided by volume of the solid part. You may need the support structure, you may not need a support structure, as I said, based upon the type of the process. If you need the support structures, then you will have volume of the internal support structures, volume of external support structures, and at the solid you also would need the external support structures. If you are hollowing the part, you need to have internal support structures just like a roof, otherwise it will just collapse. So you need to have built certain internal support structures right at the time of process planning, and that's what has been attempted and done in the whole of the process. Now the question comes is that you can do this optimization, which we have done in the virtual workbench. The algorithms are written and genetic algorithm is used in order to find out what is optimum theta x and theta y, determining like this. So the process starts, take the CAD model, follow the model, and so on and so forth, and then there are algorithms which actually evaluate and estimate what is the value of all these performance parameters. They put that together and then it starts finding out and gets you optimum theta x and theta y. But that would be dependent upon what values of W1, W2, W3 you have chosen, the weightages. So it is here, it gives a flexibility, but we also gave a measure. The flexibility is such that the manufacturer can tune W1, W2, W3 in such a way that whether he would like to put more bias on productivity or more bias on the quality or more on material utilization, he can put those bias of W1, W2, W3, and accordingly it will start determining what is the optimization. But here we gave also one interesting methodology how to optimize the weightage itself. So what we thought is that we would give what is called as performance deterioration coefficient, meaning thereby that if you give 100% weightage to one of the criteria, then for example build height, you will be producing minimum build height, but you would be losing on other two parameters, namely the percentage utilization or the stair-step error. So in this situation we found that when you have a combinations which are other than 100%, the performance of each one of them is going to deteriorate from what is minimum achievable like this. So we defined a coefficient like this, PD, called as process response divided by minimum achievable process response. That we call as PD. So we have three PD measures, PDH, PDM and PDRA and PDPM. That means how the three will be doing. Those three you can collapse into one again to say that overall performance deterioration coefficient. You could also have, so there is some sort of a double layer of optimization. We try to determine W1, W2 or X1, X2, X3 in order to minimize the overall performance measure. So whole of the algorithm works in this way. You propose this one, you minimize this, you go back into that, choosing this W1, W2, W3, do the optimization to calculate theta x, theta y. So there is a double layer of optimization which goes in that, and finally it comes out with what would be the oriented model which is going to be there. It has sliced, it has all the type of contours for each layer, it has a toolpath planning, and that can be essentially passed on to the machine for the purpose of fabrication. We tested this on variety of things. Typically the algorithm runs like this. You choose a CAD model, then you do for the propose this particular chromosome which creates a population for the GA. Here the chromosome is nothing but the two orientations which we are trying to find out. Optimum orientation. Apply the following algorithm. Design the support structures for each orientation. I put FDM primarily because FDM process needs a support structure. If you are using some other process which is a powder or liquid base, you don't need to do that. So it needed design support structures. Crossover and mutation to create a new population, which is essentially to see that new blood is put into the population in order to do this particular type of situation. Then you evaluate the fitness function, rank the solutions, go to the next population and either iterate or terminate based on the criteria what you have chosen. So in this way, in an evolutionary way, the whole thing it will keep on determining and it will start essentially finding out what are the optimum orientations so that further parts are moved. I will show you some two typical results which are essentially being done. Say the cow, one of the complex components. Look at the three blue circles. They essentially bring out that if you give 100% weightage to those criteria, 100, 010, 001, essentially shows that the three performance parameters for build height, stair-step error and percentage utilization essentially come in a diagonal way, which are the minimum achievable values. Needless to say that in those lines, the other criteria are gone haywire. But if you see the next one where you have put equal weightage to all the three criteria, you would be essentially getting this. So this essentially tries to demonstrate that tuning those weightages, you can also get to whatever is the desired output during the process of manufacturing. Then we get into the overall performance deterioration coefficient and experiment on this particular thing in order to come to what would be the criteria to come to the weightages which essentially further will give this particular type of thing. Similar situation is there for biomedical part where it tries to determine the three, and then you can see that further experimentation gets you to the scenario which is finally the chosen based on the manufacturer's requirement. You know, as we always say, the taste of pudding lies in eating it. So as a manufacturer and person, you would always like to see that what you have generated, whether it translates into a part or not. And that's really a test in order to see that what you have done, what your algorithm is showing, what you are simulating actually results in a part. So we just took that horse as a component, as a complex component. It went through the whole algorithm. We did the simulation, and actually on the SLS machine, the component was made, as you can see on the left side, the entire component was made as a monolithic component. But in order to see whether it has done the requisite hollowing and rest of the operations, we slice the component using the Wirecut EDM machine, and the two things are shown on this side, which essentially demonstrate that you can see the hollowing part which it has done in a complex way in the three-dimensional contour, which is obtained like this. We ran a couple of prototype components like this, which essentially demonstrate the whole thing. So in conclusion, I would say that the process planning strategy which we have proposed optimizes three different parameters, namely the productivity, part quality, and the cost or material utilization in an integrated manner. And another important part, since it is in the computational domain, we say that it is a generic methodology which is applied to all the AM processes needing both internal and external supports. So this methodology can be essentially done. So I thank you, and I will be glad to answer any questions and queries.